Okay, I have a question for you, and it starts with a block of cheese.
I was wondering when we were going to address the cheese situation. I saw the photo you posted, and it was frankly alarming.
It's relevant, I promise. Just bear with me.
Yeah,
So, picture this. It is Tuesday. I am walking through my kitchen, minding my own business, just trying to get to the coffee machine.
right.
And I trip over a box, this massive, heavy box. I look at the label, it's addressed to me. I open it up, and you are not going to believe this. It is 40 pounds of sharp cheddar.
40 pounds, that is an aggressive amount of dairy.
Yeah.
Like, that is not a snack. That is infrastructure.
It looked like a car battery made of cheese, and I'm standing there totally confused thinking, did I sleep shop? Is this some sort of cry for
A
help?
dairy-induced fugue state.
Exactly. But then I check my phone. And it's my smart fridge, my beautifully integrated, connected home ecosystem.
Sure.
Oh, yes. Apparently, the little sensor in the dairy drawer got blocked by a rogue bag of spinach. So the fridge algorithm read zero inventory. It panicked, calculated my average consumption incorrectly, I might add, and decided to, quote, optimize my supply chain
By ordering a bulk restock.
by ordering a lifetime supply of cheddar.
I mean, in its defense, it was trying to save you from a cheeseless existence.
Yeah.
That is a benevolent system. It just went a little wrong.
See, benevolent, that is exactly the word. It's a system acting with absolutely zero context, but total confidence. And it actually got me thinking about networks in general. Because, we are completely obsessed with them.
We are. We want everything connected.
Right. We want the fridge talking to the grocery store. We want the watch talking to the insurance company. We love this idea of a seamless, interconnected web where every single node helps every other node.
It's the ultimate dream of the superorganism. Efficiency, cooperation, the whole being greater than the sum of its parts. I mean, it is why we love the internet. Or, well, why we used to love the internet.
Exactly. And that brings us to the topic for today's deep dive. Because for the last 30 years or so, if you're listening to this, you have almost certainly been told a story about the ultimate network.
The original network.
Right. Not the internet, not the smart home, but the forest. We have been told that beneath our feet, the trees are literally holding hands, that they are feeding each other, protecting each other.
Acting like a giant socialist commune.
Yes, where no tree is left behind.
The Wood Wide Web.
Wood Wide Web. It is one of the most famous ideas in modern science. I mean, it's in Avatar, it's in Ted Lasso, it's the entire plot of the Overstory.
It's basically the script for every nature documentary produced in the last decade.
Totally. And this is why we're here. You walk into the studio today with a stack of papers that honestly, it looks like a litigation file.
I brought the receipts today. Because here is the thing about that story. The story of the loving, cooperative forest. It might just be one of the biggest cases of mistaken identity in the history of ecology.
So my smart fridge ordering 40 pounds of cheese is not the only network that is malfunctioning.
Well, the forest network isn't malfunctioning. It is working exactly as intended, but it's not working for us. And it is certainly not working to be nice.
Interesting.
Yeah. Today, we are going to look at the actual data. The original 1997 study that started the whole romance, the 2023 forensic audit that tried to burn it to the ground, and these brand new 2025 mathematical models that suggest something much, much darker is happening underground.
So the fundamental question for this deep dive is the forest a family or is it something else entirely?
That is the question, and I'll give you a spoiler. The answer might be that the forest isn't a commune at all. It's a trading floor. And the traders are absolutely ruthless.
I love a good market crash. Let's dive in.
Let's do it.
So before we get to the controversy and the big takedown, we really have to set the scene. For you listening at home, we need to understand why this idea took such a massive hold on our culture in the first place. Because the Wood Wide Web wasn't just a catchy headline, it completely changed how regular people look at trees.
Completely.
I mean, I used to look at a forest and just see, wood, just logs waiting to happen, pure competition.
Right, and you weren't wrong. That was the scientific consensus for a century. Darwinian competition. Trees fighting for light, fighting for water.
Yeah.
It was a zero-sum game.
If I grow tall, I shade you out and you die.
Exactly. That was the biological rule.
And then came this massive narrative shift. Suddenly, they aren't fighters anymore. They are lovers. They are holding hands underground.
And to understand how that shift happened, we have to look at the biological mechanism. Because it's not magic. It's not a fairy tale. It is biology. It's a thing called mycorrhiza.
Mycorrhiza. Okay, break that down for us. What does that mean?
It's Greek. Myco means fungus, and rhiza means root, fungus root. It is a symbiotic relationship that is practically as old as plants themselves. In fact, evolutionary biologists think plants probably couldn't have colonized land without it.
Really? It's that foundational.
Oh, absolutely. Here is the basic economic problem a plant faces. It is incredibly good at making cash.
Cash being sugar.
Exactly. Carbon. Photosynthesis. A tree is essentially a sugar factory. It takes sunlight and air, and it prints money.
Okay. Sounds like a good business model.
It is, but there's a flaw. The tree is often terrible at going to the grocery store. It really struggles to mine the soil for heavy, immobile nutrients, things like phosphorus or nitrogen.
Okay, so the plant has the cash, but it can't get the goods. It has a full wallet, but no car to get to the supermarket.
That is a perfect way to put it. Now, fungi are the exact opposite. They are terrible at photosynthesis. They can't do it at all. They live in the dark. But they are master miners.
Because of how they're built?
Yes, they have these microscopic threads called hyphae.
How microscopic are we talking here? Because when I picture roots, I picture these big, woody, tough things breaking through concrete.
Think way, way smaller. You're talking about threads that are 1/50th the diameter of a single human hair. They are incredibly fine.
Wow.
And because they are so fine, they have massive surface area, they can squeeze into tiny microscopic soil pores that a tree root, which is basically like a blunt telephone pole by comparison, could never touch.
So they can get into the tiny cracks and mine the minerals.
Right. They mine the water, the nitrogen, the phosphorus.
Yeah.
So the tree and the fungus strike a deal.
Classic trade.
A classic trade deal. The plant gives the fungus sugar. And by the way, it gives up to 20 or 30% of all the sugar it makes. It is a huge tax.
Wait, 30%? That's a steep commission. That's like a Hollywood agent's fee plus state tax.
It is steep. But in exchange, the fungus delivers the phosphorus and nitrogen directly into the plant's roots. And this is so successful that about 90% of all land plants do this. If you walk into a forest today and you pull up a handful of dirt, you aren't just holding dirt.
You're holding the fungus.
You are holding miles and miles of these fungal threads.
Okay, so that establishes the basic partnership. Tree and mushroom working together. But that is just a one-on-one relationship. That's me hiring a contractor to fix my house. How do we get from a simple trade deal to this massive forest-wide, wood-wide web?
That leap happens when we realize the contractor is working for multiple clients.
Yeah, the contractor is double dipping.
Or triple dipping or quadruple dipping. If I'm a fungus, I don't just attach to your roots. I grow through the soil and I attach to the tree next to you and the tree next to that one.
So physically, you are linking us together.
Physically linking you. This is the concept of the CMN, the Common Mycorrhizal Network.
It's like a telephone wire connecting two separate houses.
Precisely. Now, for a long time, scientists knew the wires were there. We could look under a microscope and see the fungus on root A and the same fungus on root B. But the big question, the billion-dollar ecological question, was whether anything was actually flowing through those wires.
Right. Are they live wires or are they just dead lines?
Exactly. And this brings us to the protagonist of the first act of our story, Dr. Suzanne Simard.
Okay, 1997.
1997. Dr. Suzanne Simard publishes a paper in the journal Nature that completely explodes the field. She was working in the forests of British Columbia, and she had this hunch. She believed the trees weren't just connected, but that they were actively moving resources between each other.
But how do you actually prove that? Because you can't exactly see invisible sugar moving through a microscopic tube buried underground. Did she use tiny cameras?
No cameras. She used physics. She used a really elegant, albeit highly radioactive, method. It's actually one of my favorite experiments in all of ecology because of how incredibly clever it is.
Okay, set the scene for us.
She went out into the wild forest, real messy nature, and she found pairs of trees growing next to each other, specifically a paper birch and a Douglas fir.
Two entirely different species. That feels important.
It is very important. They aren't clones, they are different species. So she put massive plastic bags over the tops of the saplings, sealed them up tight around the trunks.
Wait, so she's got bag trees. Is she suffocating them?
No, she's feeding them gas, but a very specific type of gas. Into the bag with the birch tree, she injected carbon-14. That is a radioactive isotope of carbon.
Let's do a quick chemistry detour. Explain isotopes for a second. Why does the radiation matter?
Sure. So normal, everyday carbon is carbon-12. It's stable. Carbon-14 has extra neutrons. It's unstable, which means it decays. And as it decays, it emits radiation that we can track.
Okay.
Think of it like a neon tag or putting a bell around a cat's neck. If you see the neon tag or hear the bell, you know exactly where that specific atom originally came from.
Got it. So the birch tree gets the radioactive neon tag.
Right. And into the bag with the Douglas fir, she injected carbon-13. That is a stable isotope. It's heavier than normal carbon, so you can detect it later with a machine called a mass spectrometer, but it is not radioactive.
So birch gets the radioactive stuff, fir gets the heavy stuff.
Right. Now, the trees are in the sunlight. They soak up the gas from inside the bags. They photosynthesize. They turn that specially labeled carbon into sugar.
So now the birch is entirely full of radioactive sugar, and the fir is full of heavy sugar.
Exactly. And then she waits.
Just lets them digest.
Yes. But then, and this is the absolute genius part of the experimental design, she creates a need. She shaded the trees.
Shaded them, like she built a tent over them.
She simulated deep shade for the Douglas fir. She blocked its sunlight, making it really hard for it to photosynthesize. It was hungry, it was stressed.
She created a poverty trap for the fir tree. She basically broke its kneecaps, metaphorically speaking.
That's one way to put it. She created a gradient, a source and a sink. The birch is in the sun, making lots of radioactive cash. The fir is in the shade, starving. Then, she took a Geiger counter, a device that detects radiation, and she didn't point it at the birch.
She pointed it at the Douglas fir, the neighbor.
The neighbor. And click, 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 and the Geiger counter went off.
That must have been an incredible moment for her, just standing out there in the woods holding this machine and hearing that clicking.
It changed everything. It proved definitively that the radioactive carbon had traveled all the way from the birch leaves, down its trunk, into its roots, into the fungal network, across the underground gap, and up into the tissue of the Douglas fir.
The birch was feeding the fir.
Yes.
But wait, are we sure it wasn't just a random leak? Like maybe the birch just spilled some sugar into the dirt and the fir soaked it up?
That was the control test, and no, it wasn't just spilling. She found that the flow was bidirectional and context-dependent.
Meaning what?
Meaning it changed based on who needed it. In the summer, when the birch had all its leaves and the fir was shaded, the carbon flowed from birch to fir. But think about what happens in the fall.
The birch loses its leaves, it goes dormant, it completely stops making cash.
Right, but the Douglas fir is an evergreen. It is still green, it's still working, it's still printing money. So in the fall, Simard found the flow completely reversed. The fir started sending its carbon back to the leafless birch.
It is a reciprocal arrangement. I got you in the summer, you get me in the winter.
Exactly.
That is insurance.
That was the conclusion. The journal Nature put it right on the cover. They coined the term the Wood Wide Web. And it suggested that forests weren't just collections of solitary individuals fighting a zero-sum battle for sunlight. They were a cooperative system, a safety net.
And this is really where the romance comes in, right?
Yeah.
Because once you establish that plants can share resources, it is a very, very short step for us humans to start saying that they care about each other.
That is exactly the trajectory the media took. And to be fair to the media, Simard and her colleagues leaned pretty heavily into this interpretation over the next couple of decades. They expanded the theory significantly.
This is where we get the mother tree stuff.
Yes. They introduced the concept of the mother tree.
I have to say, I love the mother tree concept. It's very grand. It feels like mythology. It reminds me of the Tree of Souls in Avatar.
It really does. The idea is actually based on network topology.
Yeah.
If you map the fungal connections mathematically, it looks a lot like an airline map.
Okay, explain that.
You have big hubs, the O'Hares and the Heathrows of the forest. And then you have all these small regional airports. The big old ancient trees are the hubs. Because of their massive root systems, they are connected to hundreds of younger saplings.
And the theory was that these big hub trees, these mother trees, were acting like, well, like mothers, like matriarchs.
Yes, Simard's research suggested they were actually performing kin recognition.
Kin recognition, meaning they know who their babies are.
That was the claim, that mother trees could chemically identify which seedlings were their own genetic offspring and which were just random strangers that blew in on the wind. And they would preferentially funnel more nutrients, more carbon, to their own kids.
See, that implies so much. That implies intelligence. It implies memory. It frankly implies love. The idea that a tree knows its baby and feeds it.
Simard didn't shy away from that comparison at all. In a 2018 paper, she explicitly compared the shape and function of these fungal networks to neural networks in the human brain.
Whoa.
Yeah. She pointed out that the chemicals moving through the web, things like glutamate and glycine, are the exact same chemicals that function as neurotransmitters in our brains.
So if it looks like a brain and it uses the chemicals of a brain.
She argued that the forest has the capacity for intelligence, learning, and memory. She described trees warning each other.
how does a tree warn another tree?
The idea was that if a tree got attacked by, say, aphids, it would send a chemical distress signal down into the roots through the web, and the neighbors would receive it and start ramping up their immune systems before the bugs even arrived.
It is a beautiful story. It really is. I mean, if you're listening to this, you can see why everyone bought into it. It tells us that nature is inherently kind, that deep down, survival of the fittest is actually survival of the most cooperative.
It's a socialist utopia where the rich trees feed the poor trees, the old take care of the young, and everyone looks out for danger.
It makes us feel so good about the world. It frames nature as a mirror of our absolute best selves.
It does.
And I can hear the but coming in your voice. You are literally shifting in your chair. You are looking at that second folder of research you brought.
We have to talk about 2023.
The record scratch.
A massive record scratch.
Uh-huh.
In early 2023, a paper came out in Nature, Ecology, and Evolution that basically took a sledgehammer to this entire beautiful narrative.
Oh boy, who wrote it?
It was led by Dr. Justine Karst from the University of Alberta, along with Dr. Melanie Jones and Dr. Jason Hoeksema.
And these aren't just random internet skeptics, right? These are serious mycologists.
Absolute heavyweights in the field of fungal ecology. And what is so interesting is that they didn't go out into the woods and run a new experiment. They didn't bag any trees. They did a forensic audit.
Ooh, I love a forensic audit. They checked the books.
They meticulously reviewed 25 years of research on the Wood Wide Web. They looked at every single paper that claimed trees were sharing resources, warning each other, or acting like a family. And they found something deeply disturbing in the literature.
What did they find?
They called it positive citation bias.
Positive citation bias. Okay, translate that for us. What does that mean in plain English?
It is essentially a high-stakes game of telephone played by scientists.
Okay, walk me through how that works.
Here is how it happens. Scientist A goes out and does a study. The results are mixed. Maybe they see a little bit of carbon transfer, but they aren't sure if it actually helped the tree grow or if it was just a statistical blip. So in the abstract of their paper, they write honest, cautious science. They say, quote, carbon transfer was observed, but the ecological impact remains unclear.
Honest, cautious, a little boring.
Right. But then, a year later, scientist B reads that paper. And scientist B is writing their own paper, and they need a citation to support their new theory. So scientist B cites scientist A, but they drop the nuance.
Oh, I see where this is going.
They write, as shown by scientist A, trees transfer carbon to help each other grow.
Ah, they dropped the unclear. They turned a maybe into a yes.
Exactly. Then, 5 years later, scientist C comes along. They cite scientist B, and they write, it is a well-known, established fact that trees cooperate via carbon transfer.
And by the time you get to scientist D, it's the forest is a sentient socialist brotherhood.
Precisely. Karst's team analyzed the literature and found that unsupported claim statements about the Wood Wide Web that didn't actually have hard data backing them up had doubled over the last 25 years.
Wow.
The certainty went way up in the scientific community, even though the actual underlying field data hadn't changed at all.
So the story just kept getting better and better, but the evidence stayed exactly the same.
Or in some cases, the evidence was actually much weaker than people realized to begin with. Karst's team identified 3 major takedowns, 3 core pillars of the Wood Wide Web theory that they say just do not hold up to scrutiny when you look at the raw data.
Okay, let's unpack these.
Yeah.
Because if we are going to dismantle a 30-year-old beloved theory, we need specifics. What is pillar number 1?
Pillar number 1 asks a very basic question. Is the network actually widespread?
Well, yeah. You said earlier, if I pick up a handful of dirt, it's full of fungus. We know the fungus is there.
We know the fungus is in the dirt,
Mm.
but do we know it connects tree A directly to tree B?
I assumed we did. Don't we have maps of this stuff?
That is the shocker. Mapping microscopic fungal threads in wild soil is incredibly, unbelievably difficult. You have to take a soil core, extract the DNA, and then match the DNA from a root tip on one tree to a root tip on another tree, proving it is the exact same individual fungal organism spanning the gap.
That sounds tedious.
It's like trying to map the entire global internet by digging up cables in the dark with a teaspoon. Karst found that out of all the research done in the last 30 years, guess how many studies have definitively mapped a common fungal link between specific trees in a wild forest?
I don't know, 100?
2.
2.
2 single studies.
In 30 years.
In wild forests, yes. We have mapped them in pots in the lab. We have mapped them in petri dishes. But in the actual messy wild forest, 2.
So when we see those beautiful diagrams in textbooks and magazines with the glowing lines connecting all the trees,
It is an assumption. We assume the connection is there because the fungi are ubiquitous in the soil.
Yeah.
But proving that this specific thread acts as a continuous pipeline from this tree to that tree is remarkably rare. The map is mostly blank.
Okay, that is disconcerting. That's like finding out the subway map is just a guess based on where people are walking above ground.
That's a great analogy.
But let's play devil's advocate for a second. Even if we haven't mapped every single wire, we know the electricity flows, right? Simard's Geiger counter clicked. We know the radioactive carbon moved from the birch to the fir.
True, the carbon moves.
Yeah.
Nobody's denying that. But that brings us to pillar number 2. Does it help?
Right. This is the socialist utopia claim. The idea that the big trees keep the little seedlings alive.
Exactly. Karst reviewed 28 separate experiments that specifically tested this exact question. Does being plugged into the network help a seedling survive or grow faster?
And what did the data say?
The results were a mess. Only 18% of the studies showed a clear benefit to the seedling.
18%? That's terrible. What happened in the rest of them?
In most of them, there was absolutely no effect. The carbon moved, yes, but the seedling didn't grow any faster or survive any better than seedlings that were disconnected.
It's like getting a penny in the mail. Technically, you are richer, but it doesn't change your life.
Exactly. It's ecologically insignificant. But here is the real kicker. In some cases, Karst found that being plugged into the network actually harmed the seedling.
Harmed it. Like the mother tree was stealing from the baby?
Or the network itself was draining resources. You have to remember, the fungus is not a charity worker.
Right.
The fungus is a living organism. It needs to eat. It takes a cut of the sugar. If a tiny seedling is plugged into a massive hungry network, the fungus might be pulling sugar out of the seedling to feed itself rather than pumping sugar in from the mother tree.
Oh, wow. So instead of a trust fund, it's a tax.
Exactly. Karst argues that for a seedling, the network isn't always a safety net. Sometimes it's a drain, sometimes it's acting as a parasite.
That completely flips the script. We thought the mother tree was breastfeeding the seedlings, but maybe the fungus is just milking everyone.
Milking everyone is a very, very good way to put it. Keep that in mind because we are going to come back to that idea of the fungus as a farmer later on.
Okay, so the map is blank, and the trust fund is actually a tax. What about the warning signals? The talking trees. This is the one people really, really love.
Pillar number 3. The idea that trees warn each other of insect attacks. Karst looked for field evidence of this. Real forests, wild conditions. Zero.
Zero field studies.
She found 0 peer-reviewed field studies confirming that warning signals are sent through the fungal network in a wild forest.
But wait, I have read about this. The beans and the aphids, right?
Yes, you have read about it. In the lab. In greenhouses.
Yeah.
In small pots.
Yeah.
We have absolutely seen it happen in controlled environments with agricultural plants like beans and tomatoes.
Okay, so it does happen.
If you seal a tomato plant in a bag so it can't smell its neighbor through the air, and you infect it with aphids, the neighbor does react. The chemical signal goes through the shared roots.
So it happens in tomatoes.
It happens in tomatoes and pots. But a wild forest is not a greenhouse. It is chaotic. It is vast. The soil volume is virtually infinite. There are a million other signals happening. Constantly breezes, other bugs, decaying matter, rain. Kurz argues that just because a tomato can do it in a sterile pot doesn't mean a massive Douglas fir is doing it across 30 feet of messy wild soil.
Wow. I mean, this is rough. This is like finding out Santa Claus isn't just not real, but that he's actually a bill collector.
It is a harsh reality check.
Yeah.
But Kurt's point isn't that the network doesn't exist at all. Her point is that we have projected our own human morality onto it. We called it sharing and caring, when the raw data might just show leaking and stealing.
Leaking and stealing. That sounds like a terrible law firm. So the socialist utopia is crumbling. The forest is looking less like a commune and more like a chaotic free-for-all.
It certainly seemed that way in 2023. The media completely reversed course. The headlines were all, the Wood Wide Web is a myth, Simard debunked.
But, science is a conversation. You don't just drop a mic and leave the room forever. Simard is still here. She's still a leading expert. She didn't just take this lying down, right?
Absolutely not. And this is where the story gets really interesting. Because in science, when someone tries to knock down your life's work, you don't just cry about it. You double down on your data. And in 2024 and early 2025, Simard struck back.
The empire strikes back.
Exactly. She published a fierce rebuttal. It was an opinion piece titled, Response to Questions About Common Mycorrhizal Networks. And she basically argued that Karst and the skeptics are missing the forest for the trees. pun intended.
Okay, so what is her defense? Because zero field studies is a pretty hard number to argue with.
Her first point is about the standard of evidence. She argues that demanding perfect, continuous maps of microscopic fungi in a wild forest is an impossible technological standard right now. She's saying, look, the technology to map the ocean floor with a spoon doesn't exist yet. That doesn't mean the ocean isn't there.
Okay, that's fair. Just because we can't see the wires perfectly doesn't mean the phone isn't ringing.
Right. She also strongly defends the greenhouse data. She argues that you can't just dismiss lab results because the field is messy. If we see the biological mechanism in the lab, if we see the kin recognition, if we see the signaling happening in controlled pots, it is perfectly logical to assume it is also happening in the wild, even if it's harder to measure through all the noise.
It's the smoke and fire argument. If we see smoke in the lab, there is probably fire in the forest.
Exactly. But her strongest point, and I think this is the one that really resonates ecologically, is about context. She argues that Karst's forensic review completely missed the point of when the sharing actually happens.
When? Like, time of year?
No, environmental condition. Karst looked at averages across all studies, many of which featured trees growing normally in good conditions. Simard argues that the network is primarily a safety net. It doesn't necessarily kick in on a sunny Tuesday when everyone has plenty of water and light,
Oh, I see.
in case during a crisis.
Right, you don't need a massive financial bailout when the economy is booming.
Exactly. Simard says, look at the data when the trees are deeply shaded. Look at it when there is a severe drought. When the climate is rapidly shifting, that is when the carbon transfer spikes and matters most. Just because it's not happening 24/7 doesn't mean it isn't a critical survival mechanism.
So Kirst is saying, I don't see it happening on an average day. And Simard is saying, it's not for the average day, it's for the bad days.
Precisely.
Yeah.
And Simard also defended her use of the mother tree language. She fully admitted it is a metaphor. She said, I use that term to help the general public understand the complex mathematical concept of a network hub.
Right.
It wasn't meant to be a rigid, literal biological definition for every single forest on Earth.
It is really a clash of cultures, isn't it?
It is.
Simard is like the poet-scientist. She uses grand metaphors to paint this big, cohesive picture to get people to care. And Karst is the data auditor. She's checking the spreadsheets and saying, technically, line 4 doesn't add up, so we have to throw the whole thing out.
That is a perfect way to describe the dynamic. But Amo, here is where we have to pivot. Because while Simard and Karst are arguing about the field data, is it there, is it not there, is the map complete? There is a third group of scientists who walked into the room in 2025 and said, you guys are both missing the real problem.
Oh, which is what?
The math.
The math.
Evolutionary math.
Yeah.
Game theory. Because even if the trees are sharing and even if they are signaling warnings to each other, why would they do it?
Twice, because they want the forest to survive.
Evolution does not care about nice. And evolution definitely doesn't care about the forest as a whole. Evolution cares about genes. It cares about the individual passing on its DNA. And this brings us to the, what segment of the deep dive?
Okay.
Because the mathematical explanation for what is happening underground might be darker, stranger, and much more fascinating than either the socialist utopia or the debunked myth.
Okay, lay it on me. Who are these math people coming in to ruin the party?
This comes from a 2025 paper out of Oxford University and the Society for the Protection of Underground Networks, or SBUN. It was led by Dr. Thomas Scott and Professor Toby Kears. And they looked at the Wood Wide Web strictly through the lens of the prisoner's dilemma.
The prisoner's dilemma. That's the classic game theory scenario, right? Two criminals get arrested. They're in separate rooms. If they both stay silent, they get off light. But if one snitches and the other stays silent...
the snitch wins, and the silent one goes to jail for life.
Exactly.
Scott and Kears identified a massive evolutionary problem with the altruism theory. They call it evolutionary suicide.
That sounds dramatic.
Think about it logically. Trees are inherently competitors. They're stuck in the ground, fighting for the exact same sunlight, the exact same water, the exact same patch of soil.
Right.
If I am a tree and I sense aphids, and I spend my hard-earned energy to chemically warn my neighbor that aphids are coming,
My neighbor survives.
your neighbor survives. And because they survive, they keep growing. They grow taller. They shade you out. They drink your water. By helping your direct competitor, you are actively hurting yourself.
Right. In a pure survival of the fittest scenario, helping the guy who is trying to steal your sunlight is a terrible move.
It's the worst move.
Yeah.
Mathematically, a gene for pure altruism should be rapidly weeded out by natural selection. Imagine a forest with two types of trees. You have the helpers and the cheaters.
Okay, I'm tracking.
The helpers spend all this metabolic energy synthesizing chemicals and warning everyone around them. The cheaters never warn anyone. They just stay quiet and listen. They save all their energy for growing taller. Over 50 years, who wins?
The cheaters, they get all the benefits of the early warning system without paying any of the energetic costs of sending it.
Exactly. The cheaters grow taller, they produce more seeds, they take over the canopy. Eventually, the forest is full of cheaters, and the helpers go completely extinct.
Okay, so if the math says they absolutely shouldn't be helping each other, but the Geiger counters still say stuff is occasionally moving, what is actually happening?
This is the central paradox. And Scott and Kears propose three hypotheses that explain the data without breaking the fundamental laws of evolution. And none of them are friendly.
Okay, give me hypothesis number one.
Hypothesis one is called involuntary blushing.
Blushing, like out of embarrassment.
Think about the biological mechanism of blushing in humans. When you are embarrassed, blood rushes to your face.
Right.
You don't want to blush. You aren't actively trying to communicate, hey, everyone, I am embarrassed. In fact, usually you are trying desperately to hide it.
True, it's an involuntary physiological reaction.
It is a leak. It is information leaking out of your body against your will. Scott and Kears suggest that when a tree gets eaten by a bug, it's not sending a warning. It is just wounded. It is involuntarily leaking chemicals, volatile organic compounds or root exudates. It's bleeding.
So it's screaming in pain, not shouting a noble warning to its friends?
Exactly. It's releasing what biologists call damage-associated molecular patterns. And the neighboring tree isn't being told anything. The neighbor just smells the blood. It detects the chemical leak and thinks, ooh, trouble nearby. I better build some defenses.
So it's totally passive. The first tree isn't a hero, it's just a victim, and the second tree is just eavesdropping.
Right. No altruism required, just a leak and a chemical sensor. That completely explains the communication we see in the lab without requiring the tree to be nice.
Okay, that makes perfect sense. It's sad, but it's totally logical. What is hypothesis number two?
Hypothesis number two is my absolute favorite, and it actually brings us right back to your cheese incident at the beginning.
Oh, good.
It's the fungal eavesdropping theory, or as I like to call it, the livestock theory.
Okay, I actually have an analogy for this one. I was thinking about this when I was reading the research notes last night. This is the Wall Street broker analogy.
Okay, go on. Let's hear it.
So we have been thinking of the fungi as the internet, right? Just a passive dead cable that connects the computers. But fungi are living things. They have their own agency. They have their own motivation. They desperately need sugar.
Correct. They are 100% dependent on the trees for food.
So in this analogy, the fungus is the broker, and the trees are the clients. Or actually, let's be more cynical. The trees are the assets in the broker's financial portfolio.
Like this. Keep going.
So imagine the fungus, the broker, has a portfolio of 10 trees. It is physically plugged into all of them. Suddenly, tree A gets attacked by beetles. It starts crashing. Its stock is tanking. The broker sees this and panics. It says, my asset is losing value. My sugar supply is at risk.
The fungus detects the distress signal.
Right. But the fungus does not care about tree A's feelings. It cares about its own lunch. So what does the broker do? It immediately calls up tree B and tree C, the other assets in the portfolio, and says, hey, market volatility, hedge your bets, put up your insect defenses right now.
The fungus moves the signal.
The fungus moves the signal, not because it loves the trees, but because it needs to protect the portfolio. It is actively managing its livestock. It is keeping the cows alive so it can keep milking them.
Amu, that is devastatingly accurate to the biological model.
Thank you.
The Oxford paper calls this fungal eavesdropping. The fungus listens to the tree's distress, realizes its own food source is threatened, and then chemically nudges the other trees to protect the fungus's future food supply.
So the trees aren't actually talking to each other at all. They're just being aggressively managed by a ruthless fungal landlord.
Exactly. The intelligence isn't in the trees, it's in the network manager, the fungus. And it beautifully solves the evolutionary problem. Why would the fungus spend energy to help tree B? Because tree B is the fungus's meal ticket.
I honestly respect the fungus so much more now. That is pure hustle. It is not a commune. It is a hedge fund.
It really is.
Yeah.
And it makes perfect evolutionary sense. The fungus should protect its hosts. It's in its own selfish interest to keep the forest alive.
Okay, what's the third hypothesis? You said there were three. And if the last one was Wall Street, I'm genuinely scared to ask what this one is.
This is the darkest one. Hypothesis 3 is deceptive signaling. Basically, fake news.
Trees lying to each other.
The mathematical models suggest it is entirely possible. Suppose I am a tree. I am completely healthy. I am not under attack. But I am competing with you, my neighbor, for sunlight.
Okay.
Defense costs energy. If you are busy building thick bark and synthesizing toxic chemicals to fight off bugs, you are growing tall. You're wasting all your energy on weapons you don't actually need.
Okay, I might scream wolf just to make you waste your energy.
Exactly. I emit a fake distress signal into the network. You receive it, you panic, you stop growing taller to build defenses against a bug that isn't even there. I keep growing, I steal your sunlight, I win.
That is diabolical.
It's pure game theory. If lying gives you a survival advantage, nature will eventually find a way to lie.
But do they actually do that?
To be clear, we do not have definitive field proof that trees use fake news in the wild yet. We haven't caught a tree in a lie. But the mathematical models show that a biological system based on pure honesty is inherently unstable. If everyone trusts everyone, a liar eventually evolves, exploits the system, and takes over.
Wow. So we went from the forest as a loving family to the forest as a house of mirrors filled with involuntary screamers, manipulative fungal brokers, and straight-up liars.
It is a bit of a tonal shift, isn't it?
Just a bit. So, Kara, so let's bring this all home.
Yeah.
We have looked at the romance, Simard's beautiful interconnected web. We have looked at the takedown, Karst's cold, hard forensic audit showing that the map is essentially blank. And we have looked at the math, the ruthless evolutionary logic of the Oxford team. What does this all actually mean for us? Why does it matter if you and I think the forest is a family or a marketplace?
It matters fundamentally because of how we treat it. This entire debate, the whole Wood Wide Web controversy, it is really a story about anthropomorphism.
Projecting our own human stuff onto nature.
Exactly. We called it the Wood Wide Web because we as a society were suddenly obsessed with the internet. We called them mother trees because we deeply value family and matriarchy. We desperately wanted the forest to be a socialist utopia because we are frustrated with capitalism. We constantly use nature as a mirror for what we want to be.
But nature doesn't care about our metaphors.
No, it doesn't. And that is the danger. If we manage a forest, assuming it's a loving family that will just heal itself, if we leave the mother trees alone, we might make terrible conservation decisions.
Right.
If the reality is that the forest is a marketplace, a complex, highly transactional system where every single organism is fighting, trading, and leveraging for survival, then our conservation strategies need to match that reality.
We need to respect the forest for what it actually is, not what we want it to be.
Exactly. The forest isn't a commune, it's a biological marketplace. It is based on trade, negotiation, leverage, and sometimes deception. And to me personally, that is actually more beautiful.
Why? Sounds stressful.
Because it's dynamic. It is not some static, boring painting of peace. It's an active, buzzing, grinding machine of survival. It makes the fact that it works at all, that these massive, ancient ecosystems exist and thrive, even more impressive. It's not magic. It is the result of millions of years of rigorous, ruthless negotiation.
And the fungi are the ultimate winners. I am never going to look at a mushroom the same way again.
Correct.
It is not a cute little toadstool. It is a hedge fund manager in a little hat.
Basically, it's the puppet master of the entire system.
Well, this has been quite a journey. We started with my rogue smart fridge ordering cheese, and we ended up with underground fungal investment bankers manipulating the stock market.
It's all connected, systems within systems.
It really is. And, speaking of connected systems that might not be as alive as we think they are, what are we diving into next time?
Next time, we are moving from the Wood Wide Web to the World Wide Web.
Oh, no.
We are talking about the dead internet theory.
Oh, I've heard of this. The idea that 50% of the internet is just bots talking to other bots.
That is the meme. But we are going to look at the actual mathematical reality, the traffic numbers, the AI content loops, the massive click farms. We're going to find out if the human era of the internet is already over and if we are just the ghosts haunting the machine.
Great. First you ruined trees for me, and now you're going to ruin the internet. I can't wait. But before we go, if you're listening, just think about this next time you walk through the woods. If the trees are capable of lying to each other to survive, what else in nature is running a scam right under our noses?
Something to think about.
Thanks for joining us on this deep dive. See you on the other side.